Click the bell icon to get latest videos from Ekeeda.
Chapter Nature of Chemical Bond, and we are doing the topic Determination of Molecular Structure of Bromine Pentafluoride. Hello friends, in the previous lecture we have discussed about the various molecular structures of different molecules using VSEPR theory, and now based on this theory only we are going to determine what is the molecular structure of bromine pentafluoride. So let us talk about it. So now let us discuss about the molecular structure of bromine pentafluoride using VSEPR theory, and that is bromine pentafluoride can be written as that is BrF5, that is you could see over here. So in this case basically the central atom is basically the bromine atom, and bromine and fluorine both are the halogen atoms, and in this case what we have to focus is on, we have to focus on the bromine atom, because it is basically we are talking about the VSEPR theory. So that's the reason that bromine will play a very vital role in giving the molecular structure or giving the bond angle. Everything it will depend on the bromine and also to that of the fluorine. But let us talk about the bromine first. So talking about the bromine atom, so bromine has an, basically we could say that is the atomic number of bromine is 35. So that could be written as in this format, as we know that as the electronic configuration can be written as that is 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, and as we will get to know, that is the total number of electrons that we or protons that we have mentioned over here is 2 plus 2 plus 6, that is 10. And talking about this thing, 2 plus 6 plus 2, again it is 10. So out of which we have completed at least 20, but the further thing is also with remaining. So I am writing it over here as like 3d10 and 4p5. So this is what I have mentioned over here, and let us see that how can we write the electronic configuration over here. As you could see over here, as you could see that this electronic configuration is basically based on the energy level, and in the increasing order it is being written according to the Gauss principle. But I could write it in this way also, that is 1s2, 2s2, 2p6, 3s2, 3p6, then here it will be basically 3d10, 4s2, 4p5. So in this format also we could write it. So this is the final thing that I am going to express about it, that how can we determine that is the molecular structure of BrF5. So talking about the last one, that the last shell that we have, that is the outermost shell, or we could say as valence shell, it consists of basically S subshell. So S has basically only one orbital. Talking about the P subshell has basically, you could call it as 3 orbitals. So this is it, and let us fill the electrons, and let us see that how much valence is being needed, so that we could say that 5 fluorine atoms would be attached to that of bromine. So is it possible or not? Let us talk about this thing. So here it is basically 2 electrons, so 1, 2, and here basically it is 5 electrons. So how can we fill it? We can fill it with the help of the Hertz rule, and that is what we are going to talk about. That is 1, 2, 3, 4, 5. So this is the electronic configuration that I have expressed about the bromine, and this is what I have mentioned it in terms of the ground state. So I am mentioning it over here as ground state, because I have not excited the electrons. But if I observe this one, then according to the valence bond theory or VBT, it is very easy to understand that is there is only one unpaired electron, and that's the reason that only this orbital will be basically involved in formation of a bond with only one fluorine. But we are talking about that is bromine pentafluoride. That means we need basically 4 more fluorines. So that's the reason we have to give basically empty orbitals. We need empty orbitals so that we could replace, or we could place at least 1 electron in each orbital, and somehow we can make the arrangement in such a manner that 5 electrons of the individual fluorine atom that would occupy in that orbital, and based on hybridization also we could give the structure of it, we could determine the structure of it. But talking about this one, we can't determine it. So that's the reason that we have to excite the electron, and let us do it, and let us talk about it. So for excitation of electron, we need vacant orbitals. So in this case we have no vacant orbitals, but we can write it as like 4d0, We can express the above electronic configuration in terms of this also. So now that will be the main helpful thing that we could able to do. So let me talk about this one. So we are talking about basically the outermost shell, and in this outermost shell basically 4s orbital or 4s subshell has been involved, 4p subshell has been involved, and as well as 4d subshells are been involved. And talking about this thing, that is the s, as you know, s has only one orbital, so that is what I am expressing over here. P has basically 3 orbitals, that is what we know, and we have did various of the examples also so as to express what is the reason behind this one. And talking about that is the d orbital. So d orbital consists of, or d subshell consists of basically 5 orbitals. So this is 1, 2, 3, 4, and this is the 5th one. So there are basically 5 orbitals as you could see over here. So now basically we need basically at least 5 that is unpaired electrons, and or we could say 5 incomplete that is orbitals which consist of only 1 electron. So meanwhile if we observe this one, so because basically I am talking about this only, that is 4s2, 4p5 and 4d0, and I have to shift the electrons over here. And so that is the reason. Suppose if I shift this electron, so there will be basically 2 empty orbitals that will be left, not completely but incomplete orbitals will be left over here. Then I will, if I remove this one, then there will be 3, and this one there will be 4, and somehow I could get basically 5 empty or incomplete orbitals filled with basically 1 electron in each one. So what I'm doing is I'm just keeping this one as it is, that is this 2 electron as it is. I'm shifting this electron to the d orbital that we have. So what I'm considering is I'm considering this electron to be in a black one, as you could see over here, just as to make you understand that that electron has been shifted, and that electron has been shifted on this one. So this is the one. So meanwhile if I observe this one, so this will have 1 electron here, and if I suppose if I shifted this electron, that is also I have represented in a black one, so that electron will be shifted on the d orbital, that is from 4p it will transfer to that of 4d orbital, and this is what we have. And the rest of the thing, it has been as it is. So this is the red one that I am talking about, or this is the electron that I am talking about, as you could see over here. It's very simple to understand now, but this is only occurring if we will excite the electron. So therefore this is the thing that I have did it by excitation of the electron, or this is what we could say as excited state. So this is what we have got over here, and we have got basically, as you would see, that 5 empty orbitals, or we could say like 5 incomplete orbitals that we have got, and which, as we have said earlier also, that is 1 electron will be present in each of the orbital, and that is how we can have got basically an opportunity so as to fill that is 5 electrons of the fluorine, each of the electron are of fluorine, and that is how it can be replaced. So now this is how we have got basically, as you would see, 5 incomplete orbitals, and now in that process we could fill up the fluorine atoms in here using VSEPR theory. And let us talk about this one. So what we had is we had an involvement of basically a 4s orbital, that of 4p also, and that of 4d also. But in 4s orbital, because as we could see the electron were not being shifted, and that's the reason that the electrons that are being present in this 4s orbital, as we could see over here, will become like a as I could say, like a lone pair of electrons. They are not been involving in any kind of bonding. But meanwhile, if I am talking about the p orbital, so suppose if I am representing this p1 in this way, as you could see, 3 orbitals are being present over here, while in d basically only the 2 are being involved. So I am not expressing all the next of the 3 orbitals, so I am just involving this one just as to understand. And now let us start it. So the electrons that we have filled over here, and it was basically 1. Here also it was 1, and here it was also 1. And talking about this one, this were the shifted electrons during the excited state. So when I am talking about that is BRF5, so this is what I am talking about. So suppose if I am talking about fluorine is the one basically which has an atomic number of 9. So I could express the electronic configuration as 1s2, 2s2, 2p5. And again, if I talk about the atomic orbital, so this is what I have, and it consists of 2 electrons over here. And for the p orbital, basically we have basically 1, 2, 3, 4, and this is what I'm representing it with. This is the fifth one. So 1, 2, 3, 4, and this is the fifth one, that is I'm going to represent over here. But meanwhile, this electron, actually this is the one that is responsible for bonding with that of the bromine. So this is somewhere the electronic configuration of bromine that we have excited over here. So similarly, we have got basically 5 empty orbitals or 5 incomplete orbitals, as you could see over here. So that's the reason that we are going to fill up the 5 electrons. Each electron will be of fluorine. So now in this case, basically 1 electron will be of fluorine, the first fluorine, second fluorine atom, third, fourth, and fifth. So by this, actually by this theory, that is by VSEPR theory, we have got to know that is the hybridization that has been involved in this case is basically S, P3 and D2. So this has been involved in formation of, basically we could say, BRF5. So that is what, this is what I wanted to express, and this is basically sp3d2 hybridization that has been exhibited by the bromine atom in the formation of, that is, BRF5. But now let us understand about the structure of it, because this is the main concept that we are going to talking about in this chapter, and let us talk about it in this way. So I'll express it in this way, that is this was the lone pair of electron or unpaired, this was the unpaired electron of, that is bromine, that is this red one, while this blue one, it was the electron of that of fluorine. So that is the reason that these are the bonding pairs. Even this is the bonding pair, this is the bonding pair. So here how we could say that there are 5 bonding pairs of that would be involved in the bonding of bromine and that of fluorine. But meanwhile, when I'm talking about this one, this is the lone pair of electron that has been not involved in giving a bonding to anyone. So now it plays a very vital role. How? If you look at the sp3d2 hybridization, and as if we know the geometry that has been showcased by the sp3d2 hybridization, it is basically square planar bipyramidal. Square planar bipyramidal, that is what we could get. So that is the thing that the expected, as I would write it over here, that is the expected geometry it would be basically square planar bipyramidal, having actually the same thing, that is a 90 degree of angle, the bond angle would be 90 degrees, so that is fine. But what we have got is we have got a lone pair of electron on the bromine that has been left out. So in this case, basically, if I would see, or if I would make a structure for that, so in this case I will get to know that is the bromine is the one that is being present in the middle, or it is basically the central atom, and that is what it is. And talking about, we have, as actually we have discussed earlier also, let me explain to you for a while. That is, this is the bonding pair, again this, and there are basically 5 bonding pairs. So therefore I could say that is 5 fluorine atoms can easily attach with this one, and this is the 4 fluorine atoms that I have mentioned over here. And talking about this is the one that will be at I could say like an equatorial position, and so this is what we have. But we are missing out something. Yes, we are missing out the lone pair of electron that I wanted to showcase, and that is basically this one. So this is how I would represent it over here. I will represent it here as the lone pair of electron bromine, just as to showcase that this is the VSEPR theory, and we need the geometry of it. And suppose if I have mentioned the geometry, then this is how I could see that this 4 fluorine atom are basically present on the plane. Or talking about this fluorine atom that is present above the plane, and that makes like a pyramidal structure if you observe. So that is a pyramidal structure, and even though suppose if any of the atom would have been involved over here, then that would be an expected like this square planar bipyramidal structure. But since there is no atom over here that we know, so that's the reason what we could see is we could see a square planar pyramidal structure. So this is what we have, and because of we know that this is a lone pair of electron, obviously this will have an effect on the bonding pairs over here. But the thing is, the fluorine is more electronegative, and that of the fluorine which is present over here, and this is the electron that we have, and obviously that will have an effect on it, but not that much. So that is the reason the structure will remain as it is, and the expected bond angle, it would be basically the 90 only. But talking about the geometry that we have got, or the structure that we have got, it is basically, as I have said earlier also, it is square planar pyramidal structure. So this is the expected one that we have got over here. So VSEPR, as we have got to know, it gives us a much more better detail in spite of knowing what would be the hybridization, but still after analysis we have got to know that is somewhere the lone pair also affects the geometry of a particular molecule. So this is what we have explained about this thing. So that is what I wanted to showcase. So thank you friends for watching this video. I hope you have understood this video very clearly and you have understood the concept of that is VSEPR theory, and that's it. So thank you friends for watching this video. I hope you have understood this video and you will share this video with your friends, and just don't forget to subscribe Ekeeda channel. Thank you so much.